In this presentation, I'm going to talk about the first half of 8.3. We're going to talk about electron configurations and learn why electrons are located where they are in an atom. So what we mean by electron configuration is it's just a description showing which orbitals an electron is occupying. So just to give you a brief overview of the vocabulary that's important, we're talking about the orbital and then the number of electrons in the orbital. So the orbital is a letter and the number of electrons is a number and it is a superscript. And the 1s would be the orbital, so it's in the s subshell, first level, so this would be our principal quantum number is a 1. And we are looking at a hydrogen atom. And so hydrogen only has 1 electron. And so it's really simple to solve for the shape and description of a hydrogen atom, and we did that in the last chapter, and you'll see that it's a little more difficult for multi-electron atoms. So one of the things that we found if we add another electron is we have to look at its property called spin. And so in the Stern-Gerlach experiment, what happened was electrons were kind of shot through magnetic field. So you could envision this as a bar magnet with a hole in the middle, and there's a south pole and a north pole. And the electrons go shooting through here, and you would think they would all just hit the end, but they don't. What happens is the electrons actually equally split. So some electrons travel toward the south pole and some toward the north pole, which means that they have to have a magnetic property of some sort. Okay, so when we talk about spin, we're talking about is the electron rotate, is the angular momentum of the electron in alignment with the magnetic field or not. And so it's not like a top spinning around. So electron spin becomes really, really important when figuring out quantum numbers. Pauli found he stated his principle of no 2 electrons in an atom can have the same 4 quantum numbers. So the implication of this is that if the electrons in an orbital have the same n, l, and m sub l, electrons must have opposing spin. So what is the maximum number of electrons that can be contained in each orbital? It must be 2, because electrons can only have a spin up or spin down. So that means that in an orbital, the maximum number of electrons you can have is 2. So let's take a look at how we can keep track of our electrons. So here we have our element and the configuration, and here's our orbital diagram. And so we have our n, and we have the 2 options. If you have an n of 1, an l of 0, and an m sub l of 0, your only options are plus a half and minus a half. And so electrons have mass, charge, and angular momentum. So again, it's not like a top spinning around. It's this angular momentum. Is the electron aligned with the magnetic field to give a positive spin, or is the electron aligned against the magnetic field, a negative spin? You also might hear this called spin up and spin down, and we indicate that with these arrows. So sublevel energy splitting is a concept that we need to understand in order to fill these electron orbitals. So what this means is, for a multi-electron atom, you can see how the 1s and then there's the 2s and the 2p, they have different energy. So the 2p orbitals are higher energy than 2s. So when we looked at hydrogen in the last chapter, we found that all of these energy levels were the same. They were degenerate. That is not the case for a multi-electron atom. So these 2p orbitals are all degenerate. They're at the same energy, but the 2p orbitals have more energy than the 2s orbital. So we look at our principal quantum number. So 1, 2, 3, and then we've got our L, the angular momentum. So we've got the S, P, D. So we use letters instead of numbers so that we don't have something like 3, 2, that would be confusing. So we have our principal quantum number as a number, and then our L we designate with a letter, S, P, D, F, and we won't really go much further than that, but after F they just go in alphabetical order. So something to notice here is that our 4s and our 3d orbitals are not in the order that you might think energy-wise. So our 4s orbital is actually lower energy than 3d. And this works because these are actually distribution maps. They don't have discrete boundaries, which means that when we say an electron is in the 4s orbital, what that means is it has a space in which the electron might be. So if you've ever used GPS to find your route for somewhere, and you know, when you open Apple Maps or Google Maps or whatever, and you see your little blue dot and there's that big circle around your blue dot that's shaded, so that's the probability. So your location is somewhere in that shaded circle. That's what an orbital is for an electron. So it is just this area in which an electron could exist. It is a probability distribution map. So what gives the energy to these orbitals? Well, there's these three rules, really, or three features: Coulomb's law, shielding, and penetration. So Coulomb's law describes the attractions and repulsions between charged particles. So the potential energy depends on the charges and the distance. So if we've got two pieces, two particles, it depends on both their charge and the distance by which they are separated. And here's the equation. So if this epsilon value is a constant, and 1, 4, and pi are numbers as well, so this is just a numerical factor. So you can simplify your equation, call it K, so that's this number here. And then Q1, Q2 are your charges, and R squared is the distance squared. So if we apply Coulomb's law, we can predict the behavior of two particles of the same charge and of different charges. So if we have two particles of the same charge, two particles of different charge, or charges of the particles increases, what do we see? So if we have two negative numbers, then we work this out and you'll get a positive. If you have a positive and a negative and you multiply them together, you get a negative value. And if you have a positive and a negative, but you have this 2, you actually double the magnitude. Okay? So what we see is that electrons are attracted to the nucleus because we have a negative electron and a positive nucleus, so we have a positive attraction. The farther from nucleus, the lesser the attraction. And again, that's because we have this, the farther away we get, the bigger the distance. Okay. The greater the charge, the greater the attraction. That comes from this here, the 2. And then electrons will also repel each other, because just as electrons are attracted to the nucleus because they have opposite charges, electrons have the same negative charge, so they will repel each other. Okay, so shielding. This is actually a implication of Coulomb's law, and so since according to Coulomb's law, like charges repel each other, what we see is that these electrons in the inner orbital can actually shield the outer electrons from the nucleus, meaning the outer electrons don't see the full positive charge at the nucleus because there's some negative charge in the way. So we call this, instead of just the nuclear charge with Z, we call it Z effective, and that's the total amount of attraction an electron would have for the nucleus, and it takes into account this barrier of negative charge that lessens the overall effect of the nuclear charge. So what shielding does is some electrons in the lower energy levels prevent other electrons from feeling the full attraction of the nucleus. So penetration's a little bit of a weird one, but don't worry about it. Just, you can kind of think about it as the English equivalent for the word. It's not really a different concept. So as outer electrons, they have to actually enter the energy level of the inner electrons in order to feel the complete charge of the nucleus. So here we have a ion. So we've got a 3+ charge and 2 electrons in here. So this electron outside of this shell would experience a +1 charge because you've got a 3+ and 2-. Whereas this guy here, because he's fully inside, experiences the full 3+ charge. So that kind of makes sense, right? So this is shielding, this is penetration. And the order of penetrability is the S, then the P, then the D. So basically what we're saying is it's easier for an electron to penetrate into the S orbital than the P orbital, and easier P orbital than the D orbital. So this penetrability becomes really, really important when we start talking about upper energy levels. So electrons penetrate and fill 4s orbitals more easily than 3d. This is a weird thing that we start to see. So 1s, 2s, 2p, 3s, 3p, that's all normal. And then instead of going to 3d, we go to 4s, then 3d, 4p, 5s, 4d. So this zigzag pattern kind of is how the electrons fill these orbitals. So let's do a quick concept check. So if an orbital that penetrates into the region occupied by core electrons is more or less shielded from nuclear charge. Okay, so let's think about this. If we've got an orbital going into the region occupied by the core electrons, it's going to feel the nucleus more. So it would actually be less shielded. So does that make sense? Once you have an electron fully within that inner region, it can access the full charge of the nucleus. So it would be less shielded. Okay, so to sum up, what gives orbitals their energy? Coulomb's law, which describes the attractions between charges and how they are attracted to each other. Oppositely attracted, opposite charges are attracted to each other, same charges repel. And the farther away you get, the less the attraction. Shielding is when an inner orbital prevents electrons from an outer orbital feeling the full attraction of the nucleus. And then penetration happens as electrons experience a greater effective charge as they get closer to the nucleus.